In the last class, we had an overview of embedded systems. Today, we shall look at embedded hardware, and in course of next few lectures, we shall explore hardware of embedded systems in more detail. Embedded system hardware, the basic task is to receive input, process it, and provide output. So the basic hardware is built to meet the requirement of the information processing system of the embedded appliance. The information processing system basically would consist of a processor and the other peripherals to maintain and manage input and output interfaces. Basically, the processors are microprocessors and microcontrollers. But in comparison to general purpose computing platforms, here the considerations are energy efficiency, and I would like to have instruction sets which can provide high code density. Obviously, the energy efficiency lead to enhanced battery life and less power consumption. High code density would lead to less requirement of program memory. We are all familiar with microprocessors, and microprocessors like Intel Pentium is used as a CPU for the computers that we use. Typically, a microprocessor does not have any RAM, ROM, I/O on the chip itself. The family of 8086 processors from Intel, of which Pentium is an example which we are using today in the PCs, as well as Motorola 68000 series. These are all examples of these kind of general purpose microprocessors. And a typical computer is built around this microprocessor having these as an architecture. And this is an example of a general purpose microprocessor system. Then what is a microcontroller? Basically, a microcontroller is a device which integrates a number of the components of a microprocessor system onto a single microchip. A microcontroller on its core must have the CPU, memory, and some parallel digital I/O and many other peripherals as well. So let's look at a basic block diagram of a microcontroller. What we have got? We have got the CPU, we have got memory, and we have got I/O, all connected via bus. And all these things are integrated onto the same silicon real estate. So they are on the same chip itself. There are other components of microcontroller as well. Typically, a timer module allows microcontroller to perform tasks for certain time periods. You know how the timer is typically used in a general purpose computing platform. A timer is programmed to work for a certain time period with respect to the system clock. And after that, typically a timer can generate an interrupt to the processor so that there can be switching from one task to another task. The similar function is performed by the timer on microcontroller used for embedded applications as well. We have on top of parallel I/Os, serial I/O ports, which can allow data flow between the microcontroller and devices which support serial interfaces. The serial ports are also used for interfacing with the PC during development environment and development life cycle of the embedded system. As well, when we need to use the embedded appliance with the PC to maybe read data or reprogram it, the serial port is also used. Further, we have analog to digital converters on microcontrollers to convert the external inputs which may come in the analog form to the digital form for subsequent processing by the microcontroller. We also have, in many cases, DAC, the digital to analog converter, to provide the output to the external world. So now we have got a more detailed block diagram of a program is expected to be stored. I have shown data memory as a separate entity. There are parallel ports, there are serial ports, as well as counters and timers. Now, why I have shown program memory and data memory separately? In many cases, my program memory can be actually a read-only memory or a erasable PROM or even flash, which is expected to be a persistent storage. That means when an embedded system comes pre-programmed, the program part is stored in the program memory, and which is not typically RAM. The data part of it is typically expected to be RAM, random access memory, and here it is not a persistent store. Otherwise, also you may find later on, and we shall discuss later on, there are differences in organization of program and data memory with respect to the processor core. Parallel ports are primarily targeted for interfacing with the devices. Serial ports function I have already discussed. Counters and timers to take care of different timing requirements for the embedded system. Now, the question is, we have found that microprocessors we have used for general purpose computing, and we are saying that microcontrollers are being used in many cases for special purpose embedded computing. The question is, why microcontrollers? Obviously, the dominating factor in this case is low cost and the small footprint that it offers. Since embedded systems are supposed to perform specific tasks, we do not need facilities of general purpose computing on a microcontroller targeted for embedded systems. So, we can have multiple peripherals integrated together onto a single piece of silicon to get a chip which has got a smaller footprint as well as less power consumption. We will find that on microcontrollers, on the chip itself, we have a number of I/O capabilities, because I need to interface external devices which are sensors as well as actuators, and it provides for easy integration with external circuits. And foremost, as I already stated, since I am having single purpose usage, I can manage with less sophistication on the processor hardware itself. That is why I have other peripherals integrated onto it, get a complete system with a small footprint, with smaller power consumption, and that is basically the reason why I go for microcontroller for embedded system design. Now, we shall review computer architecture before we go into details of this microcontroller architecture, because that would provide us the proper background and perspective. All of us are familiar with classical von Neumann architecture. Here what I have got? I have got CPU and I have got program and data memory put together and having a single bus connecting the two. I provide address from the CPU to the memory to fetch instruction as well as to fetch data, and we use the bus to read the data as well as write the data onto that memory. In fact, there is no difference between the data and instruction in von Neumann architecture. Both program and data memory is connected to the CPU by the same address and data bus. So, what happens as a consequence? We can get a bottleneck because getting instructions may interfere accessing RAM for data. So, I need to have distinct cycles on this bus for getting instruction as well as getting or writing data. The other typical feature is that we have the same bus, and hence the instruction and the data word is typically of the same bit width. Now, with this background, we shall look at a variant of this architecture. This is called Harvard architecture. The fundamental difference in the Harvard architecture is that I have got a program memory different from that of the data memory. And I have shown here two distinct buses connecting my CPU to the program memory and data memory. And interestingly, since I have two distinct buses, their bit widths can be different. It can be, I have shown here an example where the program memory can have 12, 14 or 16 bits, while the data memory can be simply having a bus width of 8 bits. What is the advantage of this? The advantage is, just look at this structure. I can fetch an instruction from the program memory, because program memory is typically expected to store the program. And while I am actually doing a processing, let us assume I have got some data in the CPU and I am doing some processing, and then I need to store the result. And where shall I store the result? I shall store the result in data memory. Now, while storing the result in the data memory, I shall be using this bus, and during that time period this bus is actually free. So, I can use this bus to fetch instruction. So, the instruction pipelining is facilitated by this Harvard architecture, and this is the advantage of Harvard architecture over von Neumann architecture. And you will find many of these modern microcontrollers are built around Harvard architecture. Next, we come to the concept of CISC. CISC is a complex instruction set computer. A Pentium processor, which is used in your PC, is an example of a CISC processor. What are the characteristics of CISC processors? In fact, your 8086 and other family of the other processors of that same family, 68000, they are all satisfy the properties of CISC. What are the characteristics of CISC? A large number of instructions are typically found in the repertoire of the CISC processor, and they actually perform various complex tasks. And these instructions are typically of different length and different format, and they require in many cases different number of clock cycles to execute. Also, it supports, such processors supports a number of addressing modes. So, what we find that the basic philosophy which goes into the CISC design is the more complex operations being implemented in hardware and more elaborate way of accessing data as part of the instruction set, because that is addressing modes. Addressing modes gives you a variety of way of accessing data in the memory, and you can even have operations involving data in the memory. These are the typical characteristics of a CISC processor. On the other hand, we have RISC, or the reduced instruction set computer. As the name suggests, here the basic objective is to have less number of instructions, and instructions are designed such a way that they perform single operations that can be executed in a single cycle. Also, instructions are of fixed length. A fixed length instruction facilitates what we call instruction pipelining, because I know that if I am fetching an instruction of a fixed word, so the next instruction that I fetch, or the next byte or word that I fetch, would correspond to the next instruction, and it will not correspond to a byte or word of a previous instruction. So, I can design fetch cycles of instructions to fetch words of fixed length which correspond to a single instruction for a RISC computer. It has generally a large number of registers, And these registers can contain data and can also contain addresses. And what we say that these registers are symmetric because they can be used for address as well as data manipulation in a similar way. And your arithmetic operations, in fact arithmetic as well as logical operations for a RISC processor always involve registers. So, the operations are always involving registers and not involving memory locations directly. And once you have performed the operation, the data is stored to the memory. So, you have got stored instructions, and before performing an operation, data is loaded from memory. So, you have got load instructions. So, that is why typically RISC architectures are also referred to as load store architecture. Yeah.
Don't we have pipelining in the RISC architecture? Can we have pipelining in the RISC architecture?
You can have pipelining in CISC architecture as well, okay? But the pipeline design for a CISC architecture becomes more complex than that of a RISC architecture. Now, we shall come to architecture of a particular microcontroller, and that is PIC. And PIC is one of the leading architectures for low-end applications. What do we mean by low-end applications? Typically, the applications which require your 8-bit and 16-bit processors, or even the applications which require 4-bit processors. So, these are typically low-end applications, and PIC is one of the leading architectures for low-end applications. In fact, the basic objective with which PIC microcontrollers were designed were embedded control. PICs are RISC processors, reduced instruction set processors. It uses fewer instructions, a few addressing modes, and typically executes one instruction in one internal clock cycle. Now, why PIC was designed as a RISC processor? Obviously, the reason is that the moment I have got simple set of instructions, and if I can execute a single set of instruction in one cycle, I can actually execute a large number of operations, and I can have easy implementation of pipelining without having a complex hardware. Less complex hardware would essentially mean less consumption of silicon area as well as less consumption of power. Let us try to look at the family. In fact, it is a family of processors which have got variety of configurations. Here you will find we have shown some examples and with different numbers, because PIC is not just a single microcontroller, but a family of microcontrollers. And these 12-bit, 14-bit, 16-bit, these are different word lengths that these processors support. Let us look at this block diagram, and this is the block diagram of what we call a mid-range PIC processor. I have shown here a part of the architecture and not the complete architecture, because the complete architecture will have other components as well. Here, let us see, this is my program memory. This program memory is obviously distinct from that of my data memory. The data memory is located here. So, this is an example of Harvard architecture. I have got this program counter, and program counter is obviously generating addresses for my program memory for execution of the instruction. The interesting feature is it has got a hardware stack. Why hardware stack is there? Because when there is a call or there is an interrupt, the program counter value has to be saved to enable return to that same location. We know what for the stack is used in call in and interrupts for a general purpose microprocessors. Here the stack is implemented in hardware, and if you see here, what is very interesting, the stack area is not part of program memory or that of data memory. But typically in 8086 or such processors, stack is part of your main memory itself. This is your instruction register. Now this instruction register's basic job is to take the instruction would correspond to what? The instruction whose address is provided by the program counter. This instruction is decoded by this block to generate what is called the control and the timing signals for the internal block of the PIC processor. Here there is this oscillator or the clock, and this is a timing generation circuit with an internal RC clock. This provides a basic clock for the processor to operate. And these are the set of timer blocks that we have already talked about. We have got power up timer, then power on reset, watchdog timer, brownout timer, and so on and so forth. We shall discuss them later on. The only thing that I shall just touch upon now is this watchdog timer, because watchdog timer is a very important component of microcontrollers which are intended for embedded applications. What is watchdog timer? Say you have written a program and you are running it on a PC and it has gone into an infinite loop. When you realize that, what do? You try to stop that program, and for stopping that program you actually initiate an interrupt or a signal to the processor. Now, if such an error condition happens in an embedded application, you are not there to send in an interrupt or like a control C from the keyboard or anything of that sort. It has to take a self-correcting action, because an embedded system is supposed to work without human intervention and supposed to work for all times without human intervention. So, typically what a watchdog timer is doing is, it typically gets loaded with a particular timing parameter, that is a particular count, and it starts down counting with respect to the clock. And what is expected is the system would reset watchdog timer at regular intervals. If it does not reset and the count terminates, it should generate an interrupt. Why it is not resetting? Most probably your software has forced the microcontroller to go into some infinite loop or error condition, so that the system is not in a position to reset the counter value. This is a generic concept of watchdog timer in an embedded system. So, when the timer finishes its count and it has not been reset, it will generate an interrupt, and that interrupt will enable the system to go back to one of the known predefined states. Okay. So, this watchdog timer is a very important component. This part is primarily the ALU part for the doing arithmetic computations. And what is interesting, that you will find that this RAM area is also being referred to as register file. Okay. In fact, all these RAM locations can be actually considered as registers, and as I have already stated, a RISC processor will have a large register bank, because it will use the registers for majority of its operations. Here you will find that the same condition is being satisfied for the PIC processor. This instruction register typically will have the instruction, and it will refer to the registers for operation. So, that is why you find a bus connecting this a part of your instruction register to the address multiplexer through which the register gets selected for any kind of arithmetic operation. Okay. So, what we will find that from this register the data would flow onto the data bus, and then it will go into this multiplexer so that it can be used in ALU for various operations. Now, there are two kinds of bus structure you have found here. One is here I have got the direct address which goes in through address multiplexer to select the registers, and here you will find that directly the data 8-bit data as part of the instruction is coming to the multiplexer by which it is fed to the ALU. Now, why is this bus there? To enable to have immediate mode addressing, that is when the data is part of the instruction. And there is also a provision for indirect addressing. Now, how does the indirect addressing take place? Here if you look into it, conceptually it is that I select a register, okay, and from that register I come to what is called FSR register, and from FSR register I generate the indirect address. It is a slightly complex process. We shall come to exactly the mechanism which is used for indirect addressing when we discuss the instruction set of the processor. So, at least from this architecture, what is straightforward is I support immediate addressing, direct addressing, indirect addressing, and primarily my operations are using this RAM, and this RAM is nothing but also the same register bank that of a RISC processor. Now, we come to other parts of this same architecture. These are all integrated onto the same chip along with the previous blocks that I have shown you. These are nothing but a set of ports. Through these ports actually the external devices are to be connected, and this block contains again support for variety of peripheral devices. I am just referring to two examples. One is LCD drivers, because typically if it is a standalone device it would require an LCD display. So, on the microcontroller itself we have the integrated form of LCD drivers, so that I can directly have the LCD display interfaced with the microcontroller with minimum of additional circuitry. Similarly, I have got the other ports. Okay, you will find synchronous serial ports and as well as USRTs. This is for the purpose of having serial ports implemented for communication maybe with PC and other devices. There are a number of other timers as well. In fact, I have shown you here the 3 timers. These timers are different from that of watchdog timer. Watchdog timer is a special purpose timer. These timers are application specific timers. That means you are expected to program these timers depending on your application requirements. There is an analog to digital converter block to interface or receive analog inputs. Now, obviously, I have seen that I have got a clock generator block, and you know that all processors require clocks to work with. So, PICs also require a clock, and typically it use crystals or clock oscillators or even an RC circuit. And instruction speed is typically what we call 1/4 of clock speed. So, this is, that is, I talk about T6 cycle, which is 4 times the TCLK. So, these are the typical parameters that we refer to in a PIC architecture. So, where from this factor 4 comes in? Let us try to understand that. Before that, let us look at some examples of clock frequency. These are some family of the processors, and these are the clock frequencies with which these processors operate. here we will see that this is my oscillator clock, the basic clock which is coming in. So, if I say a 4 megahertz processor, a 4 megahertz clock input, that means essentially I have a clock whose frequency is 4 megahertz. This clock is actually internally divided or split up into 4 quadrature clocks. So, I am showing you Q1, Q2, Q3 and Q4. The whole instruction execution is managed by these 4 quadrature clocks. So, what you find is in these, just look at here. So, you have got your first T6 where you actually fetch an instruction. Let us start with this. In this, I fetch an instruction. Now, once I fetch the instruction, so I have shown it within the bracket saying PC. That means I am fetching which instruction? Fetching the instruction which is being pointed to by the program counter. In the next clock cycle, what I am doing? I am actually executing the instruction that I have fetched. Now, execution of this instruction would essentially mean what? A data movement in terms of bus demand, data movement from your register file. That movement would take place on your data bus. So, my program bus is free, so I can fetch an instruction. So, what I am fetching? I am fetching the instruction at PC plus 1. So, similarly, I have shown here when I am fetching the instruction pointed to by PC, I am executing the instruction pointed to by PC minus 1. And this is how the instruction execution takes place, and what you really realize is that in one cycle, one instruction gets executed. Is this clear? So, clock internally is divided by 4 to generate 4 quadrature clocks. So, instruction cycle consists of 4 Q cycles. PC is incremented every Q1. Instruction is fetched from program and latched into instruction register by Q4. An instruction is decoded and executed in the following Q1 to Q4. So, if I go to the previous slide, you will find exactly that is what is happening. So, in this Q1, this PC is incremented, and between this Q1 to Q4 in the next cycle, the instruction getting executed. This is typically how the instruction execution takes place in PIC. So, obviously, I can have instruction pipelining. Okay, you can ask your question.
For more efficiency, why did we only go for 4?
We have gone for 4. This is an example of an architecture by 4. This is how was the demand of the internal design, because this processor I said is a low end application. So, it is not required to support an extensive multi-stage pipelining. So, when you go to complex processor, you will find more complex multi-stage pipeline support. Here it is just a support such that I have an overlap of an instruction execution and instruction fetch. Now, you find that in this case of an instruction pipelining, fetch takes 1 cycle, decode and execute takes another cycle. So, effectively I have got 1 instruction execution and 1 fetch overlapped. There can be more complex pipelining. When we look at more complex processors, you will have more complex architectures coming in place. And there are no bus conflict because we have got essentially Harvard architecture. Now, the last point that I am showing in this slide is very important. If instruction changes PC, that is when there is a branching, extra cycle is required to complete the instruction. In fact, this is a basic problem with all pipelining. That is, whenever there is a branching, obviously my pipeline efficiency goes down. Okay? So, here I would require more than 1 cycle to complete the instruction. Now, let us look at ALU in more detail, the ALU part of the architecture that I had already seen. Now, in case of an ALU, in fact, you remember there was a register called W register. In fact, W register plays a key role in all arithmetic operations. This W register is called working register. In fact, it is very similar in concept to that of an accumulator that you have in 8085 or 8086. You have your operands either from instruction word when it is an immediate, or it can come from a register, and that is one of the operands that is used in an arithmetic operation. The other operand universally comes from the W register. Now, the output of the operation goes either to W register or to any one of the registers in your register file, depending on what is called a destination bit in the instruction. Destination bit, when it is 0, it is typically part of the W register. So, the data is stored in the W register, so that it can be used in the next instruction without being fetched from the register bank. If it is 1, it is stored in the register file. The status register is just like your flag register in your 8085. Yeah, you can have. See, what we have is that when an operation takes place, the result which goes out from ALU has to be stored in some register. Which register it is to be stored depends on the D bit. There is one particular bit in the instruction word which is called destination bit, depending on value of that bit. If it is 0, then that data is stored in the W. If it is 1, it goes to one of the registers, general purpose registers. Along with this register, there is a status register which plays a key role, just like a flag register, because flag register stores what? The status of a computation. So, in this case, status register plays that role, but status register along with arithmetic status stores other information as well. So, what we say that status register in a PIC stores arithmetic status, reset status, and memory bank select bits. What are memory bank select and what are their options and what are their functions? We shall come when we look at the memory organization. Particular interest for us, since we are considering ALU operation, are these bits Z, DC, and C. What are their functions? Z is a 0 bit. So, you know what a 0 bit is, because when result of an operation is 0, this flag is set. What is DC? This is called a digit carry bit, and this is a carry bit. What is the difference between the two? When there is if I am using an 8 bit arithmetic operation, when there is a carry from the 4th bit, I get digit carry. Why that carry is important? If I am looking at BCD operations, in a BCD operation, I need to keep track of the carry from the 4th bit, and that is why I have got a special status register to indicate that. These 2 bits are used for timeout indication as well as power down mode, and these we shall discuss when we consider the power management point or power management aspect of these microcontrollers. These bits are used for memory bank select. The memory in PIC is obviously organized into 2 areas, program memory area as well as the data memory area, and access to both are possible in each cycle because I have got the distinct buses connecting them, and that also we have already seen facilitates pipelining. In fact, PIC family has got different kinds of program memory. One possibility that we have seen already in the diagram are EEPROM, erasable, programmable, read-only memory. In fact, one-time programmable chips are EEPROM, that means they have EEPROM, but there are no windows. Why no windows? Because I can use window to erase a program through ultraviolet light. And if there are no windows, then effectively I cannot erase that. So, I get one-time programmable. In fact, they are something like a factory programmable chip. So, when we are doing a mass production of an embedded system, the software development cost goes into NRE, that is non-recurring cost, and after that I simply write that program onto the EEPROM and produce a chip, and that program is not expected to be changed ever after. And these are particularly intended for very low cost applications. So, when you buy a PIC processor, you should look for C. If there is C in its number, that means it has got an EEPROM as a program memory. The other options is flash. You can have flash also in the program memory, and when you have flash, it's typically the PIC nomenclature has got F. So, flash is what? An electrically rewritable memory actually, and it can be written even by chip and much faster to develop on. Why? Because your software can be modified and modified on the fly. That means I can get an appliance which has got a flash memory, I can update that program in the flash memory after even I have bought the system and I have used it for a year. I get upgrade of the software, and I put the upgrade of the software because I have got the system which is using a PIC processor with flash memory. This is the flexibility that use of flash memory in program area provides. And in fact, the program space for the PIC processor is different for each chip, and in fact, this is an important point to consider when you are selecting a particular processor from PIC family. Typically, the program memory is 13-bit, has got 13-bit program counter. So, what does 13-bit essentially means? In fact, it is a 8K program memory effectively. I am talking about mid-range PIC processors. There are other PIC processors range which has got a variant of this size. Width of program memory bus is typically 14 bits. 14 bits, that means this is the length of the instruction. And program memory space is divided into 4 pages of 2K each. And let us see how this organization is really managed. So, I have got the PC. PC has got how many bits? 13 bits. Okay. So, out of these 13 bits, a part of it is mapped to what is called program counter latch high register. Okay. This part is mapped to program counter latch high register, and it is connected as per the architecture. Also, you remember it is connected to the hardware stack, and through the 13-bit bus it is connected to the register bank as well. What I have shown is the individual pages which are of size 2K, individual pages which are of size 2K, and the first page typically has got your reset vector, interrupt vectors. Interrupt vectors are what? If an interrupt occurs where the jump has to take place. So, the first page is typically allocated for those purposes, and then subsequent pages are for on-chip program memory. Okay. So, your program is typically stored in these area. Okay. And what is interesting about is that this first part is separated out. Why this first part has been separated out? Because using this part I can actually do what? Jump around at various locations with various kinds of constraints imposed. The stack has got 8 level deep, typically mid-range PIC has got 8 level tip stack. That means what? It can store 8 values, 8 13-bit values. And obviously, the PC is pushed onto the stack when there is a call or whenever an interrupt occurs. And typically, PC latch register, that PC latch high register, is not modified when pushed to or popped from the stack. What does that mean? That means effectively you are confined to pages. Okay, the banks that are organized into, you are confined to those pages. So, this gives you a certain kind of restrictions in moving around the value of PC. Then we look at the PIC data memory. Okay. Now, data memory is organized into two parts. One is called general purpose registers. The other part is basically special purpose registers or special function registers. Now, program, since they are stored in your program memory, typically you will find that the data memory is less, because the data memory is typically to be expected as a scratch pad memory for temporary calculations and other things, and for storing the input data, okay, if it is available. And for the major part of the data, let's look at this example, that if I need to provide some background data, say some offsets is to be provided as part of the program. This offset is a permanent data, and that offset value is expected to be stored where? In the program memory and not in the data memory. Data memory is typically to store the data which is getting generated during execution of the program, and to store information which may be coming from the external devices and to be used for subsequent calculation. Special purpose registers provide variety of core functions, and here also the memory is organized into banks. If you remember, we talked about the bits in the status registers. The bits in the status register, the 3 bits that I had shown in the status registers, they are used for selection of memory banks. Typically, area that is in the general purpose registers, these banks are arranged so that it can provide greater than 96 bytes of general purpose RAM. And again, typically I am talking about mid-range processors, and again, depending on which processor that or which microcontroller you actually choose, this value would change. And SFR, or special purpose register SPR, is used to control the peripheral and core functions like indirect addressing. Peripheral control means what? That if I have to program the peripherals, set some bits on the peripherals, then we shall be using this special function registers. So, this more or less gives me the basic introduction to the core features of the processor, PIC processor. I am not talking about the complete PIC microcontroller, obviously, because I have not yet looked at the peripherals and the I/O ports. What I have looked at so far is the core processor, the CPU, its registers, how the program memory is organized, how the data memory is organized, and how instruction pipelining is implemented in PIC. We shall look at instruction set and the peripheral components in the next class and subsequent lectures. If you have any questions, now we can have them now. Yeah. See, EEPROM, erasable programmable memory, is not necessarily a one-time programmable memory. Okay, I can erase and I can reprogram it. But typically, if I have what we have on an EEPROM, we have a window by which we use ultraviolet light to clear the